Thank you po, sir.
Sige, thank you. Again, this is one of the very important component of a structural design is the estimation of the loads that are anticipated to be imposed to your structure. And actually, the structural members are proportioned to resist the load. Of course, for large loads, that will correspond to large structural members. So malalaki ang mga beam sizes mo, column sizes, if yung estimated load is malaki. So basically, your structural sizes, columns, beams, slabs, footing pads, foundation, all these sizes are dependent to the magnitude of the applied load to the structure. And again, the loads must be realistic. There must be a proper estimate of the magnitude of the loads so that we can also consider economy and appropriateness in the design. Baka sobrang laki naman yung section mo or ng sizes ng members mo, pero only to find out na ang liliit lang pala ng load. So the load is not properly estimated, no? And again, dapat merong good science o good engineering judgment, no, yung engineer. And meron siyang extensive experience so that he will be able to come up with a good estimate of how much will be the magnitude of the load that is anticipated to be imposed to the structure. And in fact, in your design courses later, you will be calculating these loads, magnitudes of these loads. And you will be using them to design the structural members of your building. Let's start with dead load. So dead loads are gravity loads. So they are vertical loads and the magnitude is constant, fixed in position due to the weight of the structural system itself and any other material permanently attached to it. So yung mga dead loads natin, ito yung mga self-weight nung mga materials. And also, the objects that are fixed or permanently attached. So kung hindi natin mamumove yung mga, let's say, stool or mga tables, if they are not movable, they are fixed in position, then they are considered dead loads. And these are typical values of the unit weight of common construction materials for aluminum, that is 25.9 kilonewtons per cubic meter, brick, reinforced concrete, structural steel, wood. These are typical values. Of course, for a reinforced concrete, this is the typical or the average, but it varies from mixture to mixture. The average or the general unit weight of concrete is set at 24 kilonewtons per cubic meter. Siyempre, yung timber material depende sa species, no? Let's say the wood is Nara. The unit weight is different from, let's say, Molave. Those are structural timber. Yun yung mga ginagamit natin for timber structures. Pero iba-iba ang density nila, no? Iba-iba ang kanilang unit weight. Depende doon sa type ng wood. But in average, it's 6.3. So these are some examples of the unit weight, and we use them to estimate the weight of the structural member. So let's say we are calculating the weight of the beam or the column. Then we need to use these average unit weight values. In your NSCP, National Structural Code of the Philippines, there is a specific chapter, section 2, and you can see there the different dead loads of different materials. Pwede kayong kumuha doon ng mga values para doon sa pag-compute ninyo ng inyong mga dead loads later, no, in your design courses. So pag nag-RCD kayo, reinforced concrete design, or kapag nag-steel design kayo, no, you can take the values of the dead loads of your materials in chapter 2 of your NSCP. So meron doon 4 na subsections, and one of the subsection is dead loads. So just to illustrate how to compute dead load, let's say you have here a floor beam 6 feet in width. This one, 6 feet, and the thickness is 4 inches. The unit weight of the plain concrete slab is 8 pounds per square foot per inch thickness. So bawat inch ng thickness ng slab, the weight is 8 pounds per square foot. The slab serves as a partition of the ceiling for the floor below. So there's a floor here, and therefore its bottom is coated with plaster. And the unit weight of the plaster is 5 pounds per square foot. Furthermore, an 8-foot high, 12-inch thick, lightweight solid concrete block wall, this one, 8 feet in height, and the thickness is 12 inches. The unit weight is 105 pounds per cubic foot, is directly over the top flange of the beam. So this is your beam again, and you have the wall on top of that beam. Determine the loading on the beam measured per foot length of the beam. So what we do is, I take 1 foot. This is a long, slender beam, right? So I only cut a certain portion. I cut it here. I take that. And the length, this length is one foot in length. So this length here is 1 foot. And what I want is, what's the weight of these total elements or total members for every 1 foot length. And of course, whatever the weight here for 1 foot, that will also be the same weight for other 1 foot length. So what I want you to understand is that this beam is a long beam, and I only consider 1 foot. Okay, so let's do that. So this is the beam, or this is the elements, and again, this is my 1 foot length. And I want to measure what is the weight of all these elements in that 1 foot length. So we start with the concrete slab. And in the concrete slab, it's 6 feet in width, multiplied by the thickness, which is 4 inches, multiplied by 8 pounds per square foot per inch of thickness of your slab. And so we multiply, and the resulting product is 192 pounds per foot. So bawat 1 foot length, the weight of the slab is 192 pounds for every 1 foot. And again, if I take another 1 foot here, the weight of the slab is still 192 pounds. Another 1 foot, it's again 192 pounds because the weight is 192 per foot length of your slab. Again, you have to observe consistency of units. So I convert this one to, I think no need to convert, right? Because this is inch and that is inch also will cancel out. So we are good. Feet and feet will cancel, and so the resulting unit is 192 pounds per foot. Next is the plaster ceiling. So there is a plaster here below. And the given is you have 6 foot or 6 feet, again 6 feet, multiplied by 5. That's the unit weight, 5 pounds per cubic foot, per square foot. And the resulting value is 30 pounds per foot. So the plaster here, the weight of the plaster beneath your slab is 30 pounds per 1 foot length. And for the block wall, this block wall, again, I need the thickness and then the height, and then I multiply it to the unit weight. So 12 inch in feet, you have 1 foot. The height is 8 feet, and the unit weight, which is 105 pounds per square feet. And again, we simplify this, we have 840 pounds per foot. And therefore, the total will be the sum of the three weights, 1062 pounds per foot. So each foot length, the weight of all the elements is 1062 pounds per foot. And so if you have, let's say, the length of the beam is 5 feet, no? Halimbawa, ang length niya is 5 feet, then we multiply this by 5 feet and we have the total weight of the entire system of elements or system of members. Another example. This is again dead load, computation of dead load. The precast T-beam has the cross-section shown, and we are required to determine its own weight per meter length. So we take 1 meter. So this is 1 meter in length. I cut this entire chunk and compute the weight of this chunk. Determine its weight per meter length. So we take 1 meter from reinforced stone concrete and 820 millimeter cold formed steel reinforcing rods. So these are your steel reinforcing rods. We use the unit weight for steel, 77.3 kilonewtons per cubic meter, and for concrete is 23.6 kilonewton per cubic meter. So basically, we simply take the area, right? The area times the unit weight will give us the weight per meter length. So all we have to do is compute the area of the section. We start with the net area of the concrete. Net area because may mga area na is occupied by the steel reinforcement. So we have to subtract the area that is occupied by the steel. And let me start with this area here, rectangle, and that will be what? 200 by, this is what? 750 plus 100 plus 300 plus 150. I think it's 1,200 meter. So this 3,150 is 450. And you have 375 plus 375, that is 650. I know, 750. So this is 1,200. The total length, it's 1,200. So it's 1,200 times 200, that is 0.2 times 1.2. And the given unit weight, that's the total area pala muna. So area muna ang kukunin natin. Next, yung area ng trapezoid, area number 2, 1/2, the upper base, it's 450. The lower base is 150. And the height is 200. And so solving, we have the area 0.06 square meter. And then for the last area, we have 150 by 500. 150 by 500. And that will be 0.075. But again, we have to subtract the area occupied by your steel reinforcements. We have 8 bars, 2, 4, 6, 8. Diameter is 20 millimeters, so that will be 0.02 meter squared, pi over 4. And therefore, we have to subtract 0.0251. And this will be the result. Area 1, area 2, area 3, we take the sum, and then we subtract area 4. And we have this value here. So again, this is the unit weight of steel and concrete. For concrete, we multiply the area times the given unit weight. And so we have the weight per meter, 8.791 kilonewtons per meter. For steel, we have the area of your steel times the unit weight of your steel. That is the weight of the steel. And so the total weight per meter length is 8.985 kilonewton per meter length. So again, it's more on area times the unit weight. And wala naman very complicated doon because we are very much good in geometry. So there's nothing difficult in calculating the area. And we multiply the area to the given unit weight to obtain the weight of the member per length. And so again, if the beam is 10 meters length, then we simply multiply this by 10 to calculate the total length of that entire beam. So this is another example. We have the floor system, and it is consists of 15 centimeter thick reinforced concrete slab. So you have a slab here, 15 centimeter or 150 millimeters, resting on 4 steel floor beams. So these are your steel floor beams, which are in turn supported by 2 steel girders. So these are your steel girders. The cross-sectional area of the floor beams and girders are 94.8 and 337.4 respectively. Determine the dead loads acting on beams CG. So CG, that is beam, what is the load? And DH, what is the load? And your girder AD, what are the loads? So given the, again, unit weight of your steel and concrete. Now we start with beam AE and DH. So this is your AE and DH. And again, we compute the slab. Yung slab, ito, nakapatong. Yung isang slab panel, syempre maghahati sila. It will be divided into, equally into 2 parts. Half of the slab panel will be carried by this beam, and the other half will be carried by your beam BF. And since we are interested on AE and DH, so kalahati lang pupunta doon. And again, we take the area, right? 3 meters at 3. So meaning tagti 3 lahat yan. 3, 3, and 3. And that will be kalahati is 1.5 multiplied by 3 over 2. Okay, 3 over 2, that's 1.5. It's half. And 0.15 is the thickness, no? Thickness of the slab. Binigay niya sa atin sa slab thickness 15 centimeter thick. So that will be 0.15 meter. Then the length, which is 1/2 of 3, and then the weight of concrete. And so the weight is, you add the self-weight of the beam. So this is only the weight of the slab imposed to the beam. But in addition to that, meron din siyang self-weight. And that self-weight is again the area multiplied by the unit weight. So the area is 94.8 square centimeters. So in meter, that is divided by 10,000. And so the total weight is 6.043 kilonewton per meter for the whole length. So if you look at DH, for example, this is your DH. This is the load per meter length. 6.043. uniformly distributed. Paano naman yung isang beam? Ito naman, BFNCG. Ang tributary area niya, meron siya kalahati sa left, meron din kalahati sa right. Kaya isang buo. Di ba? Isang buo yun na dadalin. So again, yung thickness na 0.15, then yung 3 na tributary width, and the unit weight of concrete. And then we add the self-weight again of the beam, which is 98.4 times the unit weight of steel. And so we have the unit weight, the load in your BF and CG. Paano naman doon sa girder? Yung mga girders nyo. Anong meron tayo? Siyempre, yung self-weight at saka yung load na ibibigay ng mga girder, ng mga beams sa kanila. So, di ba, ito yung girder mo. Yan yung girder. Say, girder AD. Then, meron nakapatong dito na beam, di ba? May nakapatong na beam dyan, may nakapatong na beam dito, may nakapatong na beam, may nakapatong na beam. And then, bawat beam may load na uniformly distributed. So, for AD, it will be the unit weight of your steel times the area of the girder. So, yun yung uniform load, self-weight. So, that will be your self-weight here. And so, you have 2.608 self-weight. Uniformly distributed, 2.6 kilonewton per meter. Ngayon, yung mga beams, meron silang ililipat dyan na concentrated force. So, merong 4 na concentrated force. And it is the resultant of these distributed forces. Siyempre, yung kalahati pupunta dyan, yung other half pupunta sa kabilang side. So, yung kalahati nito, yun ang pupunta doon. And then the other half pupunta sa kabilang girder. And so, yung mga concentrated loads at A and D, here, A and D, will be kalahati nung 8 meters na length. So, 4 yun. 1/2 of 8 meters, which is 4, multiplied by the uniform, that will be the concentrated force here. And then, dun naman sa kabila, sa B and C, again, kalahati ng 8. Multiply the distributed load. And so the concentrated load is 14.412. So if you look at the loading of your AD, ganito ang itsura niya. Yung A, B, C, D, meron siyang uniform load due to the self-weight, and meron siyang mga concentrated forces due to the loads from your beam. So, ganun tayo mag-compute, no, ng dead load. Okay, what about live load naman? Live loads are gravity loads of varying magnitudes and or positions caused by the use of the structure. So these may include weights of objects temporarily placed on a structure, moving vehicles, or natural forces. Now, merong mga constant live load pressure na nasa code natin. And nanggaling ito sa long observation, long study, mga history ng data. That in residential, most of the time, the live load is 1.9 kilopascals. Again, ito yung mga values, hindi ito hinulaan lang. Merong big data itong mga ito based on a long period of observation. So these are actually values from NSCP in kilopascals. So 1.9 kapag residential, pag offices, kasi mas mabigat kapag offices. 2.4 pag library, 2.9 pag mga restaurants or gymnasiums, 4.8. Yung mga storage facility 6 kapag heavy, 12. So these are all constant values for every type of occupancy. So pwede din siyang manggaling sa mga vehicle or traffic loads. And the values are actually specified in the AASHTO, American Association for American Association of State Highway and Transportation Officials specification. So meron silang handbook, and dun sa handbook pinapakita yung different live loads for bridges that is coming from traffic loads. So meron tayong mga anyan, mga standards, mga specific values for different traffic. Impact loads naman, when live loads are applied rapidly to the structure, when they cause larger stresses than those that would be produced if the same load would have been applied gradually. Impact, instant, no? Saglit. The dynamic effect of the load that causes this increase in stress in the structure is referred to as impact. Pag masyadong mabilis kasi yung paglagay mo ng load, mas malaki yung kanyang corresponding stress. And the increase due to the dynamic effect of the load is what we call impact. And we can compute that using this value. Ang case kasi natin sa mga traffic loads, 'di ba? Yung mga wheels nila nagba-bounce sa pavement. Doon sa deck ng bridge, 'di ba? Pag tumatakbo yung sasakyan, nagba-bounce yung wheel, yung gulong ng sasakyan. And because of that bouncing effect, merong merong increase in the strength due to the dynamic effect. And that is estimated using this formula, 15 over the live load plus 38.1. And that is less than or equal to 0.3. Yung additional load due to impact. Sa NSCP, meron din tayong mga values. Like I said earlier, Chapter 2 is for minimum design loads. Nandyan ang live load, dead load, earthquake, at saka wind. So, meron din tayong live load values na nasa NSCP. And ito yung mga example niyan. Kapag office, 2.4. Pag computer, in use, 4.8, and so on. So, these are different values. And actually, this is what we use in the design. So, si student kukuha ng value dyan depending on the type of occupancy. And then that value in turn will be used to calculate the load. And that load in turn will be used to design the structural members. Now in section 205.6 of the code, it states that the unit live load from NSCP table 205.1, ito yung mga value na nandito, may be reduced using the following equation for any member having an influence area of 40 square meter or more. So pwede natin daw i-reduce. By how much? Not less than 50%. Nor less than 40% for other members. So ang kailangan lang naman natin sa formula, of course LO yun yung unreduced live load na nanggaling sa table. Halimbawa, office ka, 2.4. So that is your LO. Galing sa table yun dito. Kung ang residential ka, 1.9. Yun yung unreduced. Pero pwede daw natin yun i-reduce by a certain factor. Your L is the reduced design live load and A1 is the influence area. And that is 4 times the tributary area for a column and 2 times for a beam. Tignan nyo lang yung tributary area. Ano ba yung area supported ng beam? So, yung area na yon multiply mo ng 2 kasi beam. And then, kung column naman, ano yung tributary area ng column na dinadala niya? You multiply that by 4 times kasi, that will be your A1. And you substitute it directly to the working equation to derive the reduced live load. Okay, so tingnan natin itong example. We have a 2-story building and you have an interior columns spaced 7 meters apart. The live load is 1 and we want to reduce this live load. So ano ba yung ating tributary area sa interior column? Kasi yun ang hinahanap, no? Determine the reduced live load supported by a typical interior column located at the ground level. Tributary area, syempre, ito yon. Yan ang kakainin niya, no? Dadalhin niya. So itong column na to, ito lang ang dadalhin niya. Ito naman, dahil nasa gilid siya, ito lang ang dadalhin niya. Na tributary area. So since nasa gitna yung column, edi ang laki nung sinakop niya, no? 3.5, 3.5, so 7. 3.5, 3.5, so again 7. So yan yung kanyang tributary area. 7 by 7. And therefore, you have 49 square meters. Eh, di ba kapag column, i-multiply natin ng 4. Well, FR is 49 square meters times 1. Sa roof ito sa roof. And we have 49. Pero kapag floor, ang pinag-uusapan, floor, i-multiply natin by 4, yung tributary area. So influence area A1, you have 4 times 49, then that is 196. Ang sabi ng code, dapat hindi bababa sa 40 square meters. And we are good. We can reduce it. Pag mababa sa 40 meters, no need to reduce the live load. And again, NSCP, that is 2.4 kilonewtons per square meter. And so what we have is, yung reduced live load is 2.4 times 0.25, 4.57, and yung ating influence area na 196. Simplifying, you have 1.383 kilonewton per square meter. Yun yung reduced na live load. And sabi ng code, dapat hindi bababa sa 50% yung reduction. So from 2.4 naging 1.3 na lang. No? And yung percent na natira is 57%. So okay pa siya. Kasi pag mababa na sa 50%, sobrang laki naman nung na-reduce. So kung mababa sa 50%, hindi pwede. So okay tayo, 57.64%. Yung column sa second floor live load, FF, 49 times 1.383, this one is the given unit weight doon sa floor live load natin. Reduced floor live load. And so yung total will be 67.767 kilonewtons. Ito yung area na tributary. Ito yung pressure ng live load distributed over the area. So we multiply it, we have the unit, the concentrated force in the column or the floor. Eh yung nandoon sa taas, sa roof, meron na kanina, just kukunin na lang natin yung sum. Ito yung nandun sa roof, ito yung nandun sa second floor. So yung total will be 116. So yun yung actual force na dinadala nung column, considering reduction of the load in the second floor. And then we also have wind loads. So wind loads are lateral loads produced by the flow of wind around the structure. Nagkakaroon ka lang naman ng wind load if you are blocking the direction of the wind. Pero kung halimbawa, di ba ang ginagawa natin kapag may typhoon, binababa natin yung mga tarpaulin, no? Yung mga billboards tinatanggal natin para hindi siya mag-block ng direction ng wind. Para yung steel frame, yung steel truss, hindi mag-carry ng excessive wind load. Kasi magpa-pass through lang naman yung wind doon sa structural frame nung billboard. Kaya walang masyadong wind. Kasi hindi mo naman hinaharangan yung direction niya. So magkakaroon ka lang ng significant wind load if you are blocking the wind direction. So yung wind load, nakadepende yan sa direction ng wind. Kung yan ba ay perpendicular ang impact niya sa structure or naka-incline ang tama niya sa structure. So merong effect yon sa magnitude ng wind. Sa density ng wind, kapag basa ang hangin, mas mabigat yon, di ba? And so mas malaki ang load. Kapag moist yung air. Maraming factors no na nakaka-affect doon sa magnitude ng wind. And pwedeng ang wind ay pressure or suction. Pwede siya. And actually, there's a detailed discussion of this one in your design kung paano mag-compute ng wind load. So this one, sabi natin, it depends not only on the speed. Noon kapag mabilis, hindi lang sa bilis. But of course, kapag mabilis ang wind speed, mas malaki ang load. Depende rin sa roughness ng surface. Depende rin yun sa roughness ng surface, kung saan siya tatama. At depende sa direction ng impact. So in general, the formula is 1/2 the density of air times the velocity. And you can see here, di ba? Kapag mabigat ang hangin, mas malaki ang pressure. Kapag mas mabilis ang speed or velocity, mas malakas ang wind load. And this is the wind map in the Philippines. Meron niyang mga corresponding wind velocity per location. May mga contour dito. I hope you can see the contours. In each contour, merong corresponding wind velocity. Ito yung mga na-observe nating wind velocity during extreme wind conditions. Ito yung mga may typhoon signal number 5, number 4, and we recorded the maximum wind speeds. So ito yung nakikita natin sa map. And itong mga wind speeds na yan ang gagamitin natin to compute the wind load. Hindi lang ganito kasimple ang formula, class, ha? Medyo mahaba yung formula niyan. Kasi dito ang meron lang tayo density at saka velocity. Pero ang sabi ko nga kanina, yung surface roughness, yung direction of impact, no? Yun ang may mga factors pa na pwedeng maka-affect doon sa wind load, yung magnitude ng wind load. How about earthquake? Your earthquake loads is produced when a structure is subjected to ground motion. So this is actually in response to the movement of the ground. And that is due to earthquake. So if the movement or the ground will move, not only horizontally, but there is also vertical movement of the ground, then the building will, or the structure will sway. And there are imaginary lateral forces imposed to the structure due to the ground motion. Kapag masyadong malaki ang mass nung structure mo, mas malaki din ang sway or ang earthquake lateral load. Pag maliit lang, edi maliit rin lang ang movement. Kaya nga, pag nag-design tayo ng structure as much as possible, dapat magaan lang siya, no? Huwag masyadong bigat. Kasi pag mabigat masyado, malaki din ang lateral forces na madi-develop due to earthquake. Because later, if you compute yung earthquake loads ninyo sa inyong earthquake engineering, it is dependent on the mass na mako-compute ninyo. Okay? Pag malaki ang mass, malaki din ang earthquake load. And so, again, if you want the building to be earthquake resistant, as much as possible, the elemental components of the structure must be light. No, magagaan lang dapat. And also we have zones, 2 zones in our country, zone 2 and zone 4. Sa Palawan kasi iba yung plate Ibang plate siya kumpara dito sa other provinces. So sa zone 4 medyo mataas-taas ang seismicity diyan kumpara sa zone 2. Kaya mas malalaki ang loadings ng earthquake pagdating sa zone 4 kaysa sa zone 2. Anyway, matututunan niyo lahat yan pagdating niyo sa earthquake engineering. And these are your other environmental loads. You have the impact load. So na-discuss natin yan, dynamic effect. Kapag meron din tayong blast or explosion, these are also example of impact loads. Snow load, so na-experience lang naman natin yan sa mga cold regions kung saan umuulan ng snow. Mabigat din yung snow, class, no, kapag naipon siya sa roof. So mabigat din yun. That is an additional load. And it's also imposing lateral forces sa mga walls. kapag ka naipon yung snow load or yung snow. Hydrostatic, ito naman yung mga sa tank, dams, that is imposed by water or any fluid. And then soil, geotechnical loads, pressure exerted by the soil, and then thermal loads due to change in temperature. So pwedeng mag-cause siya ng expansion or contraction ng members that again will develop internal stresses or internal loading to the member. So these are the different types of loads. Now, yung structure natin is not only subjected to one single load. In fact, it is subjected to simultaneous loading. May dead load, may live load. And in some cases, may earthquake at may wind. Siyempre, yung earthquake, di naman palagi yun. No? Wind, hindi rin naman palagi. During typhoon lang yan, mga extreme conditions. And so, meron tayong tinatawag na load combinations. Yung mga load combinations na yun, minamagnify natin sila. Magnify in the sense na minumultiply natin yung calculated loads by a certain load combination factors greater than 1. Halimbawa, dead load. 1.2 ang ginagamit natin. 1.6 sa live load. 0.5 sa snow load. Kung walang snow load, edi yan lang. 1.2 dead load plus 1.6 live load. Kung dead load lang, 1.4 dead load. Now, itong mga load combination factors na yan, nanggaling yan sa probability ng big data. So, meron kang long-term observation dyan based sa history ng structures. So, napakadami nun. And then, they perform a comprehensive probabilistic analysis to derive the load combination factors. So, mapapansin nyo, 1.2 ang dead load kasi mas madaling ma-predict yung dead load. It's more predictable. Kaya meron kang additional 20% just in case may error ka sa computation. So, yung 0.2 doon is actually factor of safety. Baka mamaya yun na-compute mo kulang. So, nung pinatayo mo na yung building dahil kulang yung, hindi pala yun yung dadali niya, mas malaki pala, di mangyayari, magko-collapse yung building mo, no? Kasi hindi naman yun yung anticipated. Ayun yung anticipated, pero hindi naman pala yun yung nangyari. Mas malaki pa pala sa anticipated. So, para kung halimbawa magkaroon ka ng error, maglalagay ka ng room for factor of safety. Kaya minapalaki natin 1.2 for dead load, 1.6 for live load. May additional na 60% sa live load. Mas malaki. Bakit? Kasi mas variable ang live load. Hindi siya predictable. Mahirap siyang i-predict. Kaya mas maglalagay ka ng malaking wiggle room or factor of safety. Sa dead load naman kasi yan, nandiyan na siya, di ba? Fixed. Kumpitin mo lang yung timbang niya, yung self-weight niya. And then yun na yun. May error ka man, maliit lang. Kaya meron lang 20% factor of safety. Pero yung live load dahil mababa ang predictability niya, naglaalat tayo ng mas malaking safety factor. Okay? So, ito yung mga different loading natin, no? Okay, class, do you have any question? Sa module number 3 natin. Yes, meron ka bang question, Mr. Holgado?
Sir, dun po sa load combinations po, question lang po, bakit po mas maliit po yung factor dun po sa dead load, pag wind load, tsaka earthquake load po?
Okay, no? Magandang question yan. Bakit 0.9 na lang yung dead load? Ganito kasi ang reason. Very extreme kasi yung case na ang dead load is in combination with wind load and in combination with live load. Siyempre may live load din dyan. Meron din itong live load. Kaso lang merong condition. Depende doon sa condition. Very rare kasi na may dead load na, may wind load pa, meron pang live load. Kumbaga sa probability, there is a slim chance that all these loads will be acting simultaneously to the structure. And so, for the purpose of economy of the design, para naman hindi over ang loading at over ang sizes, nire-reduce natin yung load factor for dead load to 0.9. 0.9 na lang. Again, may pag-aaral to, hindi to basta-basta arbitrarily assigned. Merong long statistical analysis na kinonduct dito based on a given data. That it's a rare case na sabay-sabay yung mga loading. Kaya mapapansin niyo sa NCP, what tayong may wind na, may earthquake pa, may number 5 pa na typhoon, tapos may dead load, may live load, sabay-sabay lahat yun, tapos nag-i-snow pa, no? Wala ka tayong ganung combination. Kasi nga, based dun sa history ng data natin, walang ganung nangyari. Kaya walang ganung load combination. So, itong particular load combination na ito, ganito ang mga na-derive na mga load combination factors based on the data. A series of data. And they out na rare naman na mangyari na magsama-sama itong mga ito into one loading combination. Kaya pinaliit nila yung mga load combination factors. Para sa ganun, hindi naman oversize yung mga structural members. Baka halimbawa, yung mga size ng structural members mo, ganyan kalalaki. Bakit? Kasi you are anticipating that the building will be experiencing a combination of loads na may wind load, may earthquake, may dead, may live load. Doon sa 50 lifespan ng building, di naman nangyari yun, di ba? Baka mamaya, di ba yung earthquake natin na ganito ang intensity, ang return period niya, usually mga hundreds of years. Nag-earthquake na ang magnitude ay siguro ang return period yun after 100 years pa. So bakit mo bibigyan ng mataas na frequency or mataas na load combination? Bihira naman siyang dumating. So pwede natin siyang i-consider sa load combination, but we have to reduce the other loads. Para sa ganun, we come up with a an economical load combination and also come up with a economical design of your structure. Is that a fair, Mr. Colgado? Or
Yes
you
po,
have
sir.
some
Thank you.
Any more question, class? Again, yung mga factors, merong may journal, may published journal. Pinapakita doon yung mga statistical methods kung paano din nila dinerive yung mga load combination factors. And again, because hindi naman ganun ka-frequent na mangyari yun, kaya maliliit lang yung nilalagay nila na load combination factors. Pero hindi yun arbitrary. Hindi lang kinuha na basta ito na yun. Hindi. Meron siyang statistical analysis. So, any question? Any other question, class? Okay, so kung wala, oo nga no, tama. So let me just cut this recording. Correct kayo, iba pala ang estudyante